Hi Flat Earthers, this is Zack. In the last two videos about refraction, we talked about how the sun and the moon and the stars rise and set on the flat earth by just adding the atmosphere to the model. A lot of people thought that it was great, but some people said that we contradict science and therefore our model is incorrect. And I didn't like that. Of course, when people know that you don't belong to the scientific community, they automatically think that you are stupid. So I decided to make a small experiment and show the world that we are not stupid. And we don't contradict science, it's just them who don't understand science. Please, if you didn't watch those two videos, go back and watch them now so you can follow me here. They said that if the sunlight bends because of the atmosphere, then the atmosphere will make the apparent sun look higher than the real sun, and not lower as we did, and therefore the sun will never set. I tried to explain to them that it wasn't us who made the sun appear lower or go down behind the horizon, and that it was a program called Cinema 4D. But they kept on saying the same thing over and over again. So, in this experiment we will know if the apparent sun should look lower or higher. So let's do some science. On this table I have water that represents the atmosphere and light that represents the sun. 3 points where I'm gonna place the object, and here is the object. The distance between each point is 20 centimeters. There is nothing important about these numbers for now. I'm doing it like this just to study the angles of refraction over distance, but right now you don't need to care about them, but I'm gonna show them to you anyway. The object is 10 centimeters long. The bottom of the object is 3 centimeters in diameter, and the top is 2.5 centimeters. The distance between the light and the table is 39 centimeters. I drew this in AutoCAD yesterday before the experiment, and I drew my expectations of the real and refracted shadow based on some calculations that I've been working on for the last month. And now we're gonna find out if they are correct. But let me show you what I expected to see. So as you can see, I drew the same thing that you saw on the table, and I expected the shadow of the object to act like this, with and without refraction. First, I'm gonna explain this to you, and then I will show you the results of the experiments. So stay with me. What I did was draw a lamp and 2 objects, and I also drew their shadow in relation to the source of the light. And on the same shadow of each object, I added another shadow that should be caused by refraction. According to these people who think we are lying, the shadow after we add the water should be shorter instead of longer. But my head told me that the shadow would look longer. And that means that refraction makes the source of the light appear lower and not higher. So the first shadow of object A before refraction was 8 centimeters. So I calculated that if we added the water, the shadow would be 9 centimeters and not 7 like these people think. And I did the same thing with object B, and the first shadow of object B was 14 centimeters. So after refraction, you might think it would be 15 centimeters. Or 13 centimeters if you still think like these people. But I think that it should be longer than 15 centimeters because the distance is longer, so the shadow after we add the water, of course, would be even longer, because water will lower the apparent light, so the shadow that the apparent light is going to cause will be longer than that. So I expected it to be 19 centimeters. So let's do the experiment to make sure if I am saying the truth. So I'm gonna put the objects in position A and put the water under the lights and mark the tip of the shadow with my finger so you can see the difference. Now I'm gonna remove the water so the shadow can go back to its place. As you can see, the shadow without refraction is shorter. The refraction makes the shadow longer, and that means that the water makes the apparent light lower instead of higher. Is it because of the glass? I don't think so. Right now, I don't have the equipment to do it with water only. If you have it, then do it. In either case, we win because many people say that there is a dome. So, let's move the object to position B and do the same thing. I don't know if you can see it from there, but there is a bigger difference here. I measured all the shadows after filming the experiments and I got the same result as I had in AutoCAD. Now the question is, did the glass make the shadow look longer, or did the water and the glass make it longer? As I said before, I don't know, I don't have the equipment to know, but I emptied the plates from water and tried it to see if the glass without water would make the shadow look shorter instead of longer. But the shadow is still getting longer, and the difference is very small. Then I tried it with a flat glass only, and it did the same thing. Look at the shadows, it's getting longer. And again, a longer shadow means that the apparent light is lower. Then I added the two glasses together and they did the same thing. The shadow is still getting longer. Then I added water and covered it with that flat glass, and the shadow is still longer than the real one. The laser tests that people do with glasses to see refraction are correct, but this is not a laser pointer that is pointing towards a particular object. This is a bulb, and the sun is doing something similar, so maybe this is why people are confusing the two things. I tried it with the laser, and the shadow did become shorter. It was hard for me to film, but I think you already know that. I pointed the lamp to the object, and the shadow did become shorter. But it doesn't work the same when you use a round bulb. That is the difference. Please don't believe me, do it yourself and make your own conclusions. Thanks for watching.